Hello, my name is Divian Raj and my metric number is MA23166. So for the project, we have chosen connecting rod. So the connecting rod is a critical component in an internal combustion engine. It connects the piston to the crankshaft and converts the reciprocating motion of the piston into rotational motion of the crankshaft. So during engine operation, the connecting rod is subjected to high cyclic load stress reversals and elevated temperatures. Therefore, it must have high strength, good fatigue resistance, and dimensional stability to ensure reliable engine performance. Forged connecting rods are commonly used in automotive engines because the forge process improves grain flow and enhances mechanical properties such as strength and fatigue life. However, the forging process also presents challenges including high energy consumption, material wastage due to fast formation, and high manufacturing costs. In addition, modern manufacturing industries face increasing pressure to reduce environmental impact. Issues such as excessive energy usage, carbon emissions, and material waste highlight the need for sustainable manufacturing practices. Therefore, this project focuses on proposing a sustainable manufacturing process for a forged connecting rod by considering material selection, manufacturing methods, energy consumption, cost, and environmental impact. Thank you.
Okay, for this section, I will explain the main manufacturing challenges involved in producing a forged connecting rod. Firstly, the forging process requires very high temperature and large forming forces. This results in high energy consumption, especially during billet heating, forging, and heat treatment stages. Secondly, during closed die forging, excess material known as flesh is formed. This material waste increases raw material usage and requires additional trimming processes. Next, forged connecting rods must meet very tight dimensional tolerances, especially at the big and small end. As a result, precision machining is required, which increases production time, tooling equipments, and manufacturing costs. Finally, modern manufacturing industries face increasing pressure to reduce environmental impact. High energy usage, material waste, and carbon emissions highlight the need for more optimized and sustainable manufacturing methods. So the main objective is to develop a technically feasible and sustainable manufacturing process for a forged connecting rod used in internal combustion engines. Firstly, the project focuses on selecting a suitable material that can withstand high loads, temperature, and cyclic stresses. Secondly, the geometry and design of the connecting rod are analyzed to ensure sufficient strength, durability, and manufacturability. Next, the project describes the complete step-by-step manufacturing process, including forging, machining, and heat treatment. In addition, energy consumption and production costs are evaluated for each major manufacturing stage. Lastly, sustainability aspects such as material efficiency, recyclability, and waste reduction are assessed to ensure the manufacturing process is both economically and environmentally responsible. Thank you.
Good day, everyone. My name is Kalyamani Viswanathan, and my metric ID is MA24023. So, I will present on the material selection and the design of this product actually. So, for this project, we selected 42 CRMO for alloy steel as the material for the scooter engine connecting rod. So, the connecting rod is one of the most highly stressed components in an internal combustion engine. So during this operation, it is subjected to repeated tensile and compressive loads, also high inertia forces and elevated temperatures. So therefore, the material must have a high strength, good toughness, and excellent fatigue resistance to overcome all this. So 42 CRMO for alloy steel is a widely used in automotive applications such as connecting rods and crankshaft and more. So since it is because it performs a very well under cyclic loading conditions. So one of the main reason for selecting this material is because it's a high fatigue strength, which is critical for preventing failure during long-term engine operation. So as shown in the table, the alloy steel has a yield strength between 650 to 900 megapascal and a tensile strength up to 1200 megapascal. This allows the connecting rod to safely withstand the high combustion forces transmitted from the piston to the crankshaft without a permanent deformation. So another important advantage is this alloy steel is excellent response to a heat treatment. The material commonly quenched and also tempered, which increases the strength and hardness while maintaining the sufficient toughness. This prevents brittle fracture and improves the overall fatigue life of the connecting rod. So, from a manufacturing point of view, this alloy steel is highly suitable for hot forging and machining, which are the standard process used to produce these connecting rods. So, forging improves the internal grade, full flow, increasing strength, and as you all know, so therefore, 48 CRMO for alloy steel was selected because it provides the best balance between mechanical performance, durability, and manufacturability for an engineering connecting rod. Thank you. Moving on to the next slide, I will explain on the design of this connecting rod. We specifically designed a scooter connecting rod, a scooter engine connecting rod where there is no split cap actually. So as you can see here, I have designed this connecting rod on an inventor software and attached the drawing of this road actually with the 3D model. So moving on to the features of it, the small end connects the connecting rod to the piston through the piston pin. So it is designed with a smooth bore to allow oscillating motion while minimizing the friction and wear. So the big end connects directly to the crankshaft journal in this design actually the connecting rod is manufactured as a single solid piece without a removable cap. So this type of design is suitable for small scooter designs because it offers simplicity, compact size, and reduced manufacturing complexity. Okay, so the shank is the central portion of that transfer force between the piston and the crankshaft, which is actually designed to be lightweighted while maintaining a sufficient stiffness. Fillets are added to the design actually to reduce stress, concentration, and improve fatigue life. So overall, the design is actually on simplicity, focuses on a simplicity, strength, durability, and making it more suitable for high-speed scooter engine operation. Thank you.
Hi, my name is Lee Hui and my matrix number is MA23140. Today I'm going to present about step-by-step manufacturing process of our project, which is connecting rod. Step 1 is billet cutting and heating. The production process begins with cutting our material, which is 42 CRMO4 steel bars into billet of the requirement length using a billet cutting machine. Ensuring consistent billet size and weight, the billet are then heated in a forging furnace to approximately 1100 to 1200 Celsius for about 20 minutes to improve ductility and achieve uniform temperature, reducing the risk of cracking during the subsequent forging process. Step 2 is pre-forging. After heating, the billet undergoes pre-forging operation such as upsetting and edging at temperature around 1050 to 1150 Celsius. These operations are carried out within a few seconds pre-press stroke and are used to redistribute the material evenly. Pre-forging ensures that sufficient material is available at the big end and small end of the cutting rod, improving material flow during final forging. Step 3. Closed die hot forging. The pre-formed billet is forged into closed die at a temperature about 950 to 1100 Celsius. Using a mechanical or hydraulic press, high pressure is applied for a short time to form the connecting rod shape. This process improves grain flow, which increases the strength and fatigue resistance of the cutting rod. Step 4. Trimming and normalizing. After closed die forging, excess material called flesh forms along the die edge. This flesh is removed using a trimming press while the part is still hot or warm. Trimming improves the machining accuracy, remove unwanted material, and prepare the connecting rod for further machine and heat treatment. Step 5 is machining. After trimming, the fork connecting rod is machined at room temperature to achieve the requirement dimensions and surface finish. Rough machining is first carried out to remove excess material and bring the part close to its final shape. This process is typically performed using CNC milling machine for shaping the rod body and face, and drilling machines too. Step 6. Heat treatment and inspection. The connecting rod is finally heat to get desired mechanical properties. It is heat to authentize at about 840 to 880 degrees, between 30 to 60 minutes, and then quenched with polymer or oil. Tempering is then done with a temperature of 500 to 650 degrees at 1 to 2 hours to obtain an optimal strength, toughness, and fatigue resistance. Hardness testing, dimension checking, and crack checking. Final inspection is performed to make sure the reliability and quality is alright. For the bill of material part, for the first one, connecting rod body, which is small end, shank, and big end ring. The material of this compartment is 42 CRMO4 alloy steel, frog plus QT. For the one quantity, the unit price is 18 ringgit. And the second part is small end bush, the piston pin bushing part. The material of that is bronze, and quantity also 1 pieces. The unit price is RN 3.5. And the last part is big end bearing bush. Material is bearing bronze or steel brake bearing. Also, the quantity is 1. Unit price is RM 3 ringgit. Total estimated cost per connecting rod is RN 24.5 ringgit.
Assalamualaikum and good evening. I'm Afik, metrics number MA23135. Now we're presenting about result and discussion. First and foremost, sustainability analysis. Straight to recyclable materials. The connecting rods are manufactured from 42 CRMO4 steel, which is recyclable. Alternatively, we can use aluminium, and polymers can also be considered for lightweight application, but still remains optimal for high strength hot rod engines. We also incorporate modular designs. The adoption of modular design enhance sustainability, which means that uh, instead of discarding entire assemblies, when wear occurs, only the pet or localized components are replaced. This reduce raw materials demand, lower waste generation, and minimize the environmental footprints across the product lifecycle. For the energy consumption, each stage of the process consumes energy. We will have a look at the chart on each process and its costs and energy consumption later. For now, this is data visualization of energy consumption per process. We have several processes, and each energy will be measured by kilowatt hours. Firstly, induction heating, reducer rolling, close die forging, trimming, heat treatment, and CNC machining. As you can see with the chart, we have 2.8 on induction heating, to 1.0 on reducer rolling, 1.8, 0.5, 4.5, 2.5, as you can see on the chart. Yes. Based on the chart, highlights that these difference clearly showing that while several processes consume moderate amounts of energy, as we can see, the heat treatment dominates the profile. This suggests that any sustainability improvement should prioritize furnace efficiency, like insulation upgrades or alternative quenching methods. Alright, now we'll be looking at cost per component. As you can see on the chart right now, we have the process stage, like billet preparation, forging and trimming, heat treatment, CNC machining. All these costs are estimated, of course, and taken from one of the materials website. It appears in USD, the state dollars. For billet preparation is 0.5, 50 cents. Forging and trimming takes $1.2. Heat treatment $1.5. CNC machining take $2. Convert it to ringgit Malaysia is, as you can see on the chart, we have the total per rod. Okay, for the total per rod is 24 ringgit 50 cents. Yes. Now we'll be looking at the pie chart of the per process cost per component. Uh, yeah, the pie chart visualize shows that CNC machinings account for nearly 40% of the total cost, making it the single largest contributor. Heat treatments follow closely, reflecting both its energy intensity and specialized equipment required. Billet preparation and forging are comparatively minor contributors, but they remain essential for ensuring dimensional accuracy and mechanical integrity. Alright, next is energy consumption versus cost per process stage. This is the chart that compares energy and cost at the same time. Making it easy to see which steps are expensive in terms of energy and money. Here we can see that heat treatment still maintains one of the highest costs and also use a lot of energy. Coming at the second place is CNC machining, which is use less energy than heat treatment but still cost the most. Alright, for the last part for my part is integrated discussion. Try and find ways to improve this system or making it more cost and energy efficient. Alright, the heat treatment furnace should be modernized to reduce kilowatt hour. What does it mean by that? By modernization means like upgrades such as better insulation or alternative heat treatment methods. So, like I said just now, insulation or quenching. The machining cost could be reduced by adopting near net shape forging, which is minimize the amount of material that must be removed during CNC. Reducer rolling and trimming already reduce waste, but further optimization of die design could lower flash generation even more. That is all for me. Thank you.
My name is Tavanish Gitarampalan and my metric number is MA23165. So, for the conclusion, this project successfully delivers an affordable, sustainable, ergonomic forge connecting rod for the internal combustion engine. The I-beam cross section provides an excellent strength to weight ratio and reducing initial loads while maintaining structural integrity and improving the handling, and also close die odd forging allowed by CNC machining and heat treatment ensures high precision, consistent quality, and also superior mechanical performance with improved grain flow and wear resistance compared to the cast alternative. Sustainability is supported through the use of fully recyclable 42CRMO for steel, optimized by manufacturing processes, and efficient heat treatment. Overall, the proposed design meets all project objectives and also offer a reliable and cost-effective modern automotive application. Thank you.